Hello, everybody, and welcome to your lecture number 21. Getting near the end here, just this one, and then we have 22, 23, and 24, 25. So, 23, 24, 25. So, three more after this. So, we're getting near the end. So, we have to do volcanoes after this, and then we're going to do geologic time. Then we'll be done. So, anyway, we're getting near the end of the semester, right? And we're going to be talking about the second half of earthquakes today. So we're going to be going over a lot of like earthquake damage, hazards, the dangers. I'm sure you understand that earthquakes are dangerous, but got a little bit more specifics about what's dangerous about them, what they do, and also some historical earthquakes, and talking about magnitude scales too. So anyway, I'm going to be showing you some pictures here, some really dramatic pictures, right, from Japan, 1995. Oh, my pen's not working like usual. I always forget to turn my pen on before I start the lecture. So Japan, 1995. Sumatra, 2004 was a terrible, terrible one. I don't know if any of you were really alive. Well, you're probably alive, but you probably don't remember it if you're young. But that was a terrible one. A tremendous loss of life. 190,000 people. Tremendous loss of life from the tsunamis mostly. We'll talk about that a little bit later. So, last time we talked about earthquake faulting, plate tectonics, Wadati-Benioff zones, elastic rebound theory, all that stuff. Now we're going to talk about a few things. The Gutenberg Richter law, magnitude scales, and damage. Like damage mean like hazards, earthquake hazards. Okay. So anyway, one thing you got to do, there's a link, should be a link, both on Canvas and on your in the comments section to this YouTube video. But I would like you to watch this little USGS movie that was about the Great Alaska Quake in 1964. That earthquake was the largest earthquake in American history so far. It was magnitude 9 point, can't even remember now what it was, 9.1 or something like that. It was a very, very large earthquake. So actually, San Francisco 1908 was the most, or 1906 was the most destructive, but it actually was not the largest. So 1964 Great Alaskan Earthquake is the largest. Please listen to that video. There's two questions. The first two questions from your lecture assignment are from that video. Okay. So anyway, watch that on your own time. I don't want to play it for you right now. But for one thing, the sound is kind of not so great. But anyway, remember that what causes earthquakes? It's from the tectonic stress overcoming the frictional strength along the fault plane. Okay, so there's friction along the fault plane that keeps the fault blocks in their current positions, and tectonic stress builds up. Remember, I keep doing that thing with the fork, flipping the fork, right? That's the elastic energy that builds up, and eventually it overcomes the frictional strength and it snaps. Okay. So that's actually really that whole thing. I keep doing that with the fork, flicking it, but it's really the best physical analogy I've come up with so far. I thought about this so long, trying to come up with like what's the best physical analogy for you for earthquakes, and it's really that. It's like the fork, flicking the fork. That's the best I can think of. But anyway, if anybody thinks of anything better, I'd love to hear it. But anyway, remember elastic rebound theory, right? So we have the fault blocks. And what happens with the fault blocks? The tectonic stress starts building up, and the blocks deform elastically, right? And then when the tectonic stress overcomes, that force overcomes the frictional strength on the fault blocks are able to move, and that deformation, because they're just being elastically deformed, they snap back to their original shape. And when they do that, it releases that elastic energy that had built up from the tectonic stresses. Okay, and that process is cyclical. There's a build up and release, build up and release, build up and release. Okay. Remember, again, recap, where do earthquakes happen? They happen along plate tectonic boundaries for the most part. Recap, again, what are Wadati-Benioff zones? They're those areas of the Earth, subduction zones basically, or collisional zones, where there are very deep earthquakes. It's especially subduction zones. Remember, we have normal faults, reverse faults, thrust faults, strike slip faults. Where do normal faults happen? They happen where there's tensile stress, extensional stress, mid-ocean ridges, rift zones, places like that. Where do reverse happen? Reverse faults happen. They happen in collisional zones where there's pure shear compression. Where do strike slip faults happen? They happen where there's simple shear, right? So there's offset in the force couplings. There are transform boundaries, and you get strike slip, either left lateral or right lateral strike slip faults. Okay, so that's a little recap of what we learned so far. Okay, so this is showing the movement of footwall, hanging wall, movement along a normal fault. So we're gonna have, right, there's the fault plane, and you see the footwall, and the hanging wall moves down the fault plane, right? In the case of a reverse fault, what happens? Or actually, sorry, this is a pretty good video. This is a pretty good video showing how basin and range forms. You know that basin and range, I talked about it quite a bit. It's a very, very important, basin and range is just a very, very important process that happened in our geologic history of the southwest of our country. It's the dominant feature, topographic feature that we find in the southwest. That's why I keep talking about it. It's an extensional regime that took place over the last 20 million years. There's been extension happening over the great part of our southwest of our country. A lot of extension. That's what's created basin and range. So this is a little
basin and range province is a broad region of parallel north-south oriented valleys known as basins and surrounding mountain ranges. The province was created as this area of the North American plate was stretched, fractured, and broken into hundreds of mountain blocks. Let's watch a hypothetical block undergo early rifting. Both sides of the area under tension pull apart evenly. Hot material from the asthenosphere migrates upward, causing the land surface to rise and break along fault lines into basins and ranges. Heat from the asthenosphere warms the upper mantle and lower crust, facilitating ductile deformation, thus allowing this lower part of the plate to stretch and pull thinner like taffy. The buoyancy of the warm material, in concert with the thinning of the plate, contribute to continued upward movement, creating fault-bound valleys and up-faulted mountain ranges. This is considered by some to represent early onset of rifting.
Okay, so it just shows you how the rift valleys there or I shouldn't say rift valleys, but the basin and range valleys in the southwest of our country, Nevada, Arizona, California, actually all the way up into Wyoming as well, have formed over the last 20 million years. Okay. Here we go. This is just another video here on this reverse faults. Okay, so take a look at reverse faults. So in reverse faults, the footwall is going to be on the bottom, and it's going to be the hanging wall that's going to move up along the fault line. Okay, so there's a reverse. That happens during compression. Okay. This is a little video just kind of showing a little model of compression, showing how compression forms these what are called fold thrust belts in mountain building regions. Okay, so it's a good thing, a good model to kind of understand how like maybe the Andes formed, places like that. Okay, or maybe the Tibetan Plateau, how it forms. So what they're going to do, they have all these layers of material, and they're going to slowly compress it, and you're going to see kind of what structures form. Okay, so there it goes. They're pushing the material, and you can see how the material's kind of looking like folding and thrusting, folding and faulting occurring. You can see some little faults. Okay, so they're actually drawing there in all the little faults that are forming, as long with the folds. So anyway, it's a very good model though that shows what real mountain belts look like with all their folding and thrusting faults that are occurring. Okay. So anyway, just some visualization of how these kinds of faults occur, and normal faults, reverse faults, thrust faults, etc., etc. Okay. So number 3, crustal extension is mostly accommodated with movement on what kind of faults? Those are normal faults. Okay, normal faults accommodate crustal extension, like the basin and range provinces. Crustal shortening and compression is accommodated with what kind of faulting mechanisms? That's number 4. That's where you get reverse and thrust faults. The difference between a reverse fault and a thrust fault: so a thrust fault has a low angle to the fault, reverse has a high angle. Okay. Number 5, what kind of faults do you expect to find at spreading ridges or continental rifts? Again, these are extensional regimes, so you get normal faults there. Number 6, what kind of faults would you expect to find at convergent boundaries? These are going to be, again, coming together, compression, pure compression, and you're going to get reverse and thrust faults. All right. Now, one thing I want to talk about too are something called intraplate earthquakes. So let's talk a little bit about intraplate earthquakes. What do I mean by intraplate earthquakes? Well, most earthquakes occur along plate boundaries, right? We've already discussed that many, many times. Most earthquakes are happening along plate boundaries. Some earthquakes, you'll notice, though, are not happening along plate boundaries. So if you take a look at this map, again, I've showed you this map many times now, there are some earthquakes that happen within the plates, right? So number one, I have a number 1, a number 2, and a number 3. So number 1, there's a lot happening right here. That's kind of an interesting thing because there's a lot of earthquakes concentrated right there in the middle of Africa. And then number 3, there's a lot of earthquakes kind of like in China and in the interior there. So I want to talk about those 3 causes of those 3 things. So let's talk about first, number 1, all the earthquakes that are happening in the interior of North America. There's not a lot of them, but there are some. So, there are a lot, like I said, there are a lot of faults all over the world, everywhere. It's not like there's always faults. Okay, faults don't cause earthquakes. It's the tectonic stress that causes the earthquakes. Okay, so there's always faults. So there are a lot of old faults. In fact, there's a place called the New Madrid Seismic Zone, which is here around Tennessee, Arkansas, Missouri, Kentucky, kind of where all those states meet. And it's actually can be quite active. It used to be quite an active area. Now it's died down a bit, but there's still earthquakes there. There's actually a famous earthquake that happened in 1811, 1812. It's about a magnitude 7, pretty big. And there were actually 4 magnitude 7 earthquakes that happened around then. They're actually so large they caused the Mississippi River to run backwards for a day. So that's why there's that famous book that was written about it, the day the Mississippi ran backwards. And it was interesting. It's actually really important to American history because it was seen as a sign among the Native Americans that some great change was happening. Of course, it was the early expansion of America, right, and the whole Manifest Destiny and moving out to the West. But anyway, it did play a role in American history too, so it's an interesting read. Anyway, number 2, what are some of the causes of intraplate earthquakes? So reactivation of old faults. That's the key here, right? In America, North America, there are old faults that can be reactivated. And there are things like hydraulic fracking and pumping of hydraulic fracking fluids that have reactivated some of those old faults. So you might have heard about how fracking can cause earthquakes. That's what I'm talking about. And we'll get to that a little bit more later. Intraplate earthquakes also can happen in places where there's rifting. So rifting and creating new plate boundaries. So this is happening right now in East Africa. I pointed out how there's all these earthquakes in East Africa. Where are those coming from? They're coming from the East African rift zone. The African continent is rifting apart, and pretty soon there's going to be a new plate boundary there. Okay, so that's why you have earthquakes in Africa happening intraplate. Intraplate earthquakes, I also pointed out, are happening in China and in the middle of the Eurasian continent. What's that about? That's happening from stress building up very far from the plate boundaries, from just all of the tectonic stress that's building up from the collision of India into the Eurasian continent, into Asia, and it's building up a lot of tectonic stress far away from the boundary. But it's all ultimately connected to that collisional zone. It's a tremendous, tremendous collisional zone that's going on there right now. It's a very big deal. So anyway, so those are the 3 causes of intraplate earthquakes. Another thing I wanted to say, continuing along with North America and the reactivation of old faults, fracking fluids have played a role in this. One thing that fracking fluids do is when they frack to release natural reservoirs of oil and gas, what they do is they take those old fluids and they pump them high pressure at very high pressures into very, very, very deep reservoirs in order to keep them away from aquifers, because we don't want that fracking fluid getting into drinking water. So they pump them very down very, very deep at very high pressures. And what that does is it lubricates pre-existing faults. It lubricates the fault planes. And when it lubricates them, what does that do? That takes away the friction. And remember, it's the friction that stops movement. Okay? So, again, going back to my friend the fork, okay? And I've built up elastic strength, but the friction keeps it from moving. Now imagine if I oiled my hand right now, what would happen? It would slip, right? And that's exactly what's been happening in places like Oklahoma. Look at how many 2017, I know this is 5 years ago, but or several years ago, but look at how many earthquakes there are in Oklahoma. What are those from? There shouldn't be any earthquakes in Oklahoma. It's from pumping hydraulic fracking fluids. So there was a pretty big earthquake. It wasn't huge. I mean, it was a 5.8, which is 5.8 is the point where you can cause damage, or magnitude 5. There's a very famous Catholic university there, St. Gregory's, that actually was so badly damaged it bankrupted the school. So it was a good university, but it bankrupted the school. It was just so devastating. So induced seismicity from fracking fluids. This shows you how many earthquakes there were in 2014, 2015, 2016 from the injection of hydraulic fracking fluids. So it very, very clearly shows a very, very good correlation between the amount of volume of water being pumped down and the number of earthquakes. So again, this tectonic stress was there. It just got released because it lubricated the fault planes. The fracking fluid lubricated the fault planes. So anyway, earthquakes are pretty hard to. So moving on from intraplate earthquakes and causes of intraplate earthquakes. We talked about number 10. Number 9, it says, what kind of faults are found in the New Madrid seismic zone? That area was an old rift valley, and that's what the original faults were created with there being a rift valley there. And it's about a 600 million year old rift valley. But it was a failed rift, and so it never went through. So since that was an extensional area, the real foot fault and everything associated with the New Madrid seismic zone, those are all normal faults. They're all rift faults. So extensional faults, normal faults. Now let's get on to number 11. So it says, why can't we predict the exact time an earthquake will occur? What makes an earthquake so unpredictable? So it's very, very hard for us to predict when earthquakes are going to occur exactly. Like give you a time and date. This is going to slip and fail at time, next week at 4:30 p.m., whatever. We can't do that. Okay, we can't do that. What we can do is assess hazard. So, for example, we can say, hey, in the next 50 years, there's an 80% chance that we're going to have a magnitude 9 earthquake at this particular location. Okay, we can do that. But that's all based off of history, right? We look at the history of seismic activity in that area. We find that, okay, and every 10 years, on average, there's an earthquake, magnitude 9 earthquake. So that allows us to gauge from historically, the risk level at that particular location of that particular magnitude of earthquake. Okay, so it's all based off of history. Now we can't say though what will happen for sure. Okay, so we can't say that next week at 4:30 p.m. we're going to have an earthquake. We can't do that. So why can't we do that? Because it's so hard to predict. This is why. Remember that this comes from two factors: tectonic stress overcoming frictional strength. So stress builds up, okay, and then it hits the failure strength, okay, and when it hits the failure strength, the failure stress, that's when an earthquake occurs. The stress on the fault immediately releases, and the stress goes down, and then it starts to build up again. Okay, and then it releases, and then it builds up again, and it releases, and it builds up again, and it releases, builds up again. Okay, so that's how it goes. But the thing is, we never know exactly what the failure strength of the fault plane is. Okay, because it's variable. There's variable fault strength. it can change. It's not the same always, for maybe the fault, last time the fault moved, it got itself into a very strong position, and it's not going to slip again for a very long time. Maybe it got in a very weak position. So we don't know the exact fault. We never know exactly the fault plane strength. We don't know what the frictional strength is. Also, we don't know what the background stress, we don't know how much stress is building up at any given time either. And we have no way of measuring any of that stuff either. We don't have a way of measuring the strength of a fault plane. We don't have a way of measuring the rate of tectonic stress buildup either, at least not in a reliable way. So it just makes it very unpredictable. Like I said, our best bet is to gauge hazard of earthquakes by history. So if you go to Parkfield, California, you see that every 20 some years, it seems like on average, they have a big one. Okay, they have a big earthquake. So they had one 1857, 1881, 1901, 1922, 1934, 1966, and 2004. And you can see that on average, maybe the average was something like 20 something years. But that's the best that we can really do. Okay, we can't say exactly when an earthquake is going to happen. All right, so let's get on to number 12. It's about the Gutenberg-Richter law. So Gutenberg-Richter law. You've probably heard of Richter before because you probably heard of the Richter scale before. So the Richter scale is a way of measuring the magnitude, quantifying the magnitude of an earthquake. Because in science, we always want to go towards quantifiable measurements, right? We want to stay away from subjective things and other scales like that. So the Gutenberg-Richter law, Richter law is a relationship between the magnitude of the earthquake and how often it occurs. So frequency and magnitude. I ask you, number 12, what are the two variables that are related by the Gutenberg-Richter law? It's frequency and magnitude. Now, the short story of it is this. The number of earthquakes that you get per year, it depends upon the magnitude, okay? So magnitude, basically what you find is that magnitude, looking for my pen. Okay, so magnitude 4 earthquakes are going to happen multiple times per day. A magnitude 5 earthquake is going to happen about once per day on average. Magnitude 6 earthquakes are going to happen maybe like once a week. Magnitude 7 earthquakes are going to happen maybe once a month. I'm talking about over the whole world, okay? Not just one place. Magnitude 8 earthquakes are going to happen maybe every year. And a magnitude 9 earthquake is going to happen about once every decade, okay? So magnitude 9 earthquakes are about the strongest earthquakes we experience here on planet Earth. They probably can get up to magnitude 10. But those have not happened because a magnitude 10, if you think about it, magnitude 10, if you follow that logic, should only happen about every 100 years. Okay, so in the time that we have lived here on Earth, we haven't experienced, or not lived here on Earth, but been recording earthquakes, right, in a quantifiable way. We haven't experienced a magnitude 10. We haven't measured one of those. They probably have happened, but we haven't measured them, okay? The biggest earthquake so far that's ever occurred is Chile, 1960, 9.6 magnitude, okay? All right, so an earthquake over magnitude 8 is a great earthquake. It's a very large earthquake. You're only going to get one of those per year, maybe two of them per year. Magnitude 7s are major earthquakes. Magnitude 6 are destructive earthquakes. Magnitude 5 are damaging earthquakes. Like I said, magnitude 5 is really the only thing that's gonna the smallest earthquake you're gonna write home about. Magnitude 4 doesn't really cause very much damage. Magnitude 5 really only causes slight damage. But of course, it can damage things quite a bit, but it's slight damage. Whereas magnitude 6 is really could destroy a city. Magnitude 7 can definitely destroy a city, and magnitude 8 can really devastate a place. So, and magnitude 9 can also just totally devastate. So the Northridge earthquake that I lived through was very, very destructive, but it was only a magnitude, I think magnitude 7, maybe even magnitude 6 point something. I can't remember exactly. So anyway, that's what the Gutenberg-Richter law measures. It relates the frequency with the magnitude. Now, one thing I want to say about magnitude, magnitude is a logarithmic scale. That means the magnitude differs by a factor of 10 every step you go. So a magnitude 9 releases 10 times more energy than a magnitude 8. A magnitude 8 releases 10 times more energy than a magnitude 7. Magnitude 7 releases 10 times more energy than a magnitude 6, and so on. Okay. Richter magnitude. Let's talk about different magnitude scales. So the one that you're probably most familiar with and you've heard of before is the Richter scale. Richter scale measures the amount of ground shaking. Okay, it's the amount of ground motion. The actual, and by the way, it's called ML. So ML. If you go into that earthquake database, you'll notice that there's different kinds of magnitudes given to you. So there's the Richter magnitude along with what's called the moment magnitude, which is more popular to use among scientists. But Richter magnitude is abbreviated ML, and it's equal to the log of the amplitude of the ground shaking plus 3 times the log of 8 times t, which is t is the s minus p time. That's how far away the shaking is, minus 2.92. And I know that seems like a weird equation. You don't have to know that equation. You don't have to know how to use that equation. But what I do want you to know is what two variables are involved in the Richter scale. And the answer is amplitude of the largest signal, the largest shake, and the s minus p time, which is the distance, gives you the distance from the epicenter. Okay, so basically what it is, it's just the amount of ground shaking, but it factors in how far away you are from the earthquake. And of course, it has to do that, because if you are right on the epicenter, you're going to get a lot of shaking. But if you're far away from the epicenter, you're going to get very slight shaking, right? So and of course, that's the same earthquake with the same magnitude. So we have to take the distance from the epicenter into account, or else we're going to get different magnitudes for the same earthquake, and that can't be true, right? An earthquake has a magnitude, absolutely. It doesn't matter how far away you are from the epicenter. So it takes into account amplitude and the s minus p time, which is basically the epicenter distance from the epicenter. Okay. So number 15, I'm saying, what of the three scales, describe what each one actually measures. Amplitude, Richter scale's amplitude and epicentral distance. All right, so there's Charles Richter. He died in 1985. Magnitude scales. Now, the next magnitude scale I want to talk about is actually the one that is preferred by most scientists, and it's called the moment magnitude. The moment magnitude is abbreviated MW, and it's 2/3 log mu SD minus 10.7. Okay, again, you don't have to know how to calculate that. Don't worry about that. But I do want you to know what the equation is based off of. Okay, it's based off of this. So a lot of scientists didn't like Richter magnitude. And the reason is that, ground shaking isn't actually... Ground shaking kind of depends on what kind of material the waves are moving through. So, some material will shake a lot, some material will not shake very much, but it depends, even though that earthquake released the same amount of energy. So they wanted to take different factors into account. So they came up with moment magnitude. Most of the time, moment magnitude is pretty close to the same as Richter magnitude. So, magnitude 6 on the Richter scale is probably going to be a magnitude 6 in the moment scale, but it'll be slightly different and slightly more accurate in terms of how much energy is actually released by the earthquake. Now, for a moment magnitude, what does it depend on? It depends on something called the shear modulus. think of that. You might be like, I have no idea what a shear modulus is. I don't like that word. It's a scary word. Don't like it. That's all right. Shear modulus, it's just a parameter. It just describes how easy it is to shake the material, like how easy it is to propagate a wave through that material. Okay, so some materials propagate waves better than others. Okay, and so it's just a material property that tells how easily waves travel through it. Okay, so that's what the shear modulus means. So it depends on shear modulus, depends on the fault area, the area of the fault plane, and it depends on the slip length. That means how much slip actually occurred, how much offset actually occurred during the earthquake. Okay. All right, so there are the different magnitude scales. Magnitude 9 earthquakes are the largest we've ever experienced, and they usually take place over, hundreds of fault planes that are hundreds of kilometers, maybe thousands of kilometers in size. Okay, so magnitude 9 earthquakes, very, very powerful. This is an amazing pie chart. I want you to take a look at this pie chart. It's tremendous. All right. What does this pie chart show you? It's showing you all the energy released by the earthquakes that we have recorded over like the last, maybe since 1960. So maybe like the last 80 something years. Shows you all the energy that's been released. The amount of energy that's been released, this little pie slice right here, is all the energy that's been released from all of the magnitude 5 earthquakes. This slightly larger red pie slice is all of the energy that's been released over the last 80 years by magnitude 6 earthquakes. This larger orange pie slice is all of the energy that's been released over the last 80 years by magnitude 7 earthquakes. This one is all the energy released by magnitude 8 earthquakes. Okay, so look at this. This is crazy. About, I don't know, not quite half the pie is all magnitude 5 to magnitude 8 earthquakes, magnitude 9. The rest of the energy, like 60% of the energy that's been released from earthquakes, is due to only 5 big earthquakes. Chile, 1960. Isn't that amazing? Imagine this. I mean, think about this, guys. Chile, 1960 is the biggest earthquake we've had, magnitude 9.5, moment magnitude. All right. That's like a quarter of all the earthquakes that have occurred in the last 80 years. A quarter of that energy. There's been thousands and thousands. I mean, look at that. I just go back to this map you've been looking at. Look how many thousands of earthquakes there have been. Thousands of them. And yet, a quarter of all the energy was released in one earthquake, Chile, 1960. Another big chunk of energy was released by Alaska, 1964. And then Sumatra, 2004, Japan, 2011. Look at Japan, 2011, released as much energy as all the magnitude 5 earthquakes that have occurred in the last 80 years. It's amazing. I mean, it's really amazing how much energy is released by these big earthquakes. They are awesomely huge. Awesomely huge. So anyway, just 5 earthquakes have released more energy than all of the magnitude 5s, all the magnitude 6s, all the magnitude 7s, all the magnitude 8s combined. And magnitude 8s are big earthquakes. Okay. So anyway, just find that amazing. One of the last scales I want to talk about is the Mercalli scale. Mercalli was a Italian Catholic priest who came up with this scale very early on, before we had the Richter scale and the moment magnitude scale. And he came up with this scale as a way of trying to quantify the strength of an earthquake. Italy, of course, is a very seismically active area. So Mercalli came up with this scale. that is based off of damage. We still use the Mercalli scale because it's very useful for looking at historical earthquakes before we were measuring seismic waves. So, it goes to 1 through 12. It's rated 1 through 12. And it's rated 1 through 12, and it's based off of the kind of damage that you get. So almost unnoticeable all the way to severe damage, wide cracks appear in ground, waves seen on the ground surface, et cetera, et cetera, et cetera. So it's very useful for us. We still use the Mercalli scale just as a way of quantifying historical earthquakes before the use of, and we can base it off of the damage, the reports, historical documents reporting the amount of damage seen. All right, so let's talk about hazards. This is the last question you have for your what do you call it, lecture assignment. The hazards that I'm going to talk about are shaking, fire, liquefaction, landslides, and tsunamis. So I wanted to explain. Most of these things are pretty like you know what they are. This is just a really cool video. This is in San Diego, which of course it has a lot of earthquakes. But I want you to see this all. It's really neat. This is a full-scale earthquake shake table, and what engineers can do is build buildings and test out different buildings in San Diego at the University of San Diego to see how they stand up to different magnitude earthquakes. So take a look at this. It's really neat. So here they have
researchers put a 6-story lightweight cold-formed steel building through a scaled motion measured during the magnitude 6.7 Northridge earthquake. The shaking of the wall-braced building took place on the world's largest outdoor shake table at the University of California, San Diego. This is part of a larger project aimed at understanding how cold-formed steel frame structures withstand earthquakes and fires in order to develop ways to make buildings safer in earthquakes, fires, and other disasters. Ignite a fire if they move too much during an earthquake. The appliances are both braced and freestanding to evaluate which restraint systems are most effective. This is the tallest cold-formed steel frame structure to ever undergo tests on a shake table. The researchers want to know how the 64-foot structure will perform during the series of simulated earthquakes. This type of structure is lighter than a concrete building of the same height, so it has less mass to generate damaging forces. The building will undergo fire testing after the earthquake simulations. The researcher...
Anyway, pretty neat, right? Wouldn't it be cool to work there at University of San Diego and put things on that shake table? So fires, one thing they were talking about, maybe you noticed in there, is about the water heaters and the appliances. It's a big deal because a lot of those are hooked up to gas lines, and if the gas lines break, then you get fires. Very, very dangerous. This is San Francisco, 1989, the Loma Prieta earthquake. Created a lot of fires, right? Liquefaction is something pretty interesting. When you shake, I'm kind of seeing if I have a video on liquefaction at all. That's the tsunami videos. Those are pretty horrible. Liquefaction is when water-saturated sediments lose their shear strength. And when they lose their shear strength, the buildings can just sink into them. They become like quicksand. So they could feel like very strong sediment when you're just standing there, but when they start to vibrate, it loses its shear strength, and the sand, the saturated wet sand, becomes like quicksand, and things just sink into it and collapse. Landslides, of course, can be triggered by earthquakes, and very tragically, tsunamis. Tsunamis are probably the most dangerous of all these phenomena. I wanted to show you some YouTube videos on how tsunamis are triggered by earthquakes.
Caused by the movement of the huge tectonic plates that continents sit on. And what happens is they come together, and one, in this case, the Pacific plate, is moving below the Japanese or Eurasian plate. Now it causes that plate to bend when it sticks there. There'll be a bit too much friction, it'll stick, pressure builds up until suddenly it's released and flick. Have a look at this. Now this is the tectonic plate that Japan is sat on, and here's the Pacific plate coming down underneath it. Now normally they want to move together at about 9 centimeters a year, but sometimes it gets stuck. And when they get stuck, the energy of them moving together gets translated to strain energy, literally flex and bend in these huge slabs of rock. And that energy builds and builds. They're flexing and bending more and more. When they finally slip, that stored energy, all that twist and bend in the rock gets released into sudden movement. Like that. As you can see, it literally flicks up, moving the ocean floor above it, which moves the ocean, causing a tsunami. So here we've got a bigger submarine version of what's going on. Now, this gives a representation of what's been happening 24 kilometers below the ocean surface in the Japan Trench. And these things work in what they call a stick-slip way. Most of the time they're stuck, but occasionally they slip. And that's what an earthquake is. So we've got it here, this is bent up here. It's full of pent-up energy, waiting to slip. And when the slip happens, that energy gets released into the ocean, causing a series of tsunami waves, moving in both directions across the Pacific.
So anyway, that shows you what happens during a tsunami, of course, and how an earthquake can generate a tsunami. You might have heard stories about how before a tsunami wave comes in, it seems like the tide gets very low. And that does, in fact, happen. The reason that it happens is because you have to remember that a tsunami wave is a wave. So the peak of the wave, before you get to the peak of the wave, there's the trough of the wave. And that's what that recession of the water level is that arrives sometimes before a tsunami. You might have seen things like this. These are very just terrifying videos from Japan, 2011. The thing also about tsunami waves is we're used to seeing waves, of course, if you go to the beach, that have a very small wavelength. You know, the wave is only, few meters across. But a tsunami wave is different. A tsunami wave is, kilometers across. So you don't really see it coming like a big tidal wave coming, it's going to appear more as like a very gradual increase in the water level. That it'll keep coming and coming and coming and coming and coming. So that the wavelength of these waves, it's hundreds of kilometers, so it takes time for them to actually come in all the way. So it's a wave, but it's a huge wave, okay? It's a very long wave, 100 kilometer long wave, okay? So you'll notice in this video of the Japanese tsunami, it's a 15-minute video. I'm not going to show you the whole thing, but it's a 15-minute video because it takes 15 minutes for the wave to actually come in all the way. So you might not realize it, but the wave is already coming in. It's already coming in. So nothing's unusual seems to be happening right now, but if we skip ahead, right? So you can, like I said, you can see the wave is coming in. The wave is hitting. But it's such a long wavelength, it's breaking already, but its peak has not yet arrived. Its crest has not yet arrived, but its crest is coming. So we skip ahead a few minutes. So there you go, that's still coming in. 5 minutes into it, it's still coming in. And then but then, it takes 6 minutes before it actually goes over the seawall. And then when it goes over the seawall, then, all hell breaks loose, right? But, of course, when you look out over the ocean, you don't even see the wave, right? But it's there. It just has such a long wavelength that you don't notice it, really. It looks more like just a rising sea level. So, yeah, and you can see how devastating these things are. So imagine, the sea level just suddenly rising, 30 feet. And you get a pretty good idea of what these things are like. They're just devastating, extremely dangerous. The ones in, of course, the one in Indonesia in 2004, like I said, killed 190,000 people. The one in Japan only killed around 10,000, and that was because of the early warning systems they had in place. So anyway, I think you get the idea of what these things are like. They're very terrifying. So anyway, I think I talked about where are the hot spots for earthquake hazards. You can see Corpus Christi almost has nothing. So we're very few earthquakes here. we're fortunate in that. California and the West Coast has a lot. Alaska has a lot. There's actually, you'll notice a hot spot right around the New Madrid seismic zone too. And there's a hot spot here too in Charleston, South Carolina, actually. Again, that has to do with, that whole reactivation of old fault lines. So anyway, some famous earthquakes I've talked about here. But I kind of want to keep going. I don't even have any questions about those. But, like I said, the 1964 Alaskan earthquake, you definitely want to know something about that. I asked some questions on the test about that. There's a 1989 Bay Series Loma Prieta earthquake. That actually happened. It was recorded. The earthquake happened in the middle of the World Series, and so it was actually recorded on live television. So it's pretty crazy. The last big earthquake, there's going to be a magnitude 9 at some point in the Pacific Northwest. We don't know. The last time it happened was about 1700. It's about 300 years ago. So when will the next one be? We don't know. But it very well could be in your lifetime. Okay. We find if you go to the Pacific Northwest, you can actually find these ghost forests. The trees that you see right there can be radiocarbon dated. We find that they all died about 1700. What killed them? Probably the tsunami that was generated from that earthquake, magnitude 9 earthquake off the coast of the Pacific Northwest. Okay. So anyway, some examples of exam questions will be asked in multiple choice forms. Why is it difficult to predict earthquakes? Because earthquakes cycle. They have variable stress drops, variable fault strengths, and it's very hard to predict exactly or measure what exactly the stress buildup is and what exactly the fault strength is. Can earthquakes occur inside plate interiors? Yeah, they can. We talked about some of the causes of intraplate earthquakes, interior plate within the interiors of plates. What are 3 fault magnitude scales that we learned? Moment magnitude, Richter magnitude, and Mercalli magnitude. Make sure you know what variables each one of those magnitude scales depends on. What are some examples of non-tectonic earthquakes? We talked about nuclear explosions, induced seismicity. There's mine collapse. Meteorites can cause non-tectonic earthquakes as well. What kind of hazard what kind of hazards come from earthquakes? Shaking, fires, liquefaction, landslides, tsunamis. Where do earthquakes occur in the United States? Mostly in the West, but there are a few hot spots, of course, in the New Madrid seismic zone, and in Charleston, South Carolina. There's some hot spots there. Where can we expect a magnitude 9 earthquake to happen in America next? Very possibly in the Pacific Northwest. What is a tsunami and why is it so dangerous? We talked about that as well. So here are some exam questions. The hanging wall block moves up and over the footwall block in a reverse fault. Okay. Magnitude 7 earthquakes occur 10 times more frequently than magnitude 6 earthquakes. As frequently as magnitude 6 earthquakes, or 10 times less frequently. It's 10 times less frequently. Okay. And that's the end of the show. So hope you enjoyed this lecture. I'll talk to you next time. We move on to volcanoes, 2 lectures on volcanoes, then geologic time, and then we're all done. So you have a good week. Talk to you next time.